Good morning, students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. Today I will deliver a lecture on classical mechanics. This is the first paper in MSc Previous Physics in MGS University. In my earlier lecture, I have taught you about mechanics of single particle. In that, I have derived the conservation laws of linear momentum, angular momentum, and energy. The conservation law of linear momentum arises when force acting on the particle is zero. When force is zero, P will be constant in motion. The second law, conservation law of angular momentum, was derived by using when torque equal to zero, angular momentum will be conserved. And the third law, that is the conservation of energy, arises when system is conservative in nature. Now I am extending it to number of particles. There we have only used a single particle. Here I am using number of particles. We are considering n number of particles of the system. In that case, there was only one kind of force. But here we have considered a system having n number of particles. Here the force will be of two types. One is the internal force. Here I am representing the equation of motion of ith particles. Of ith, a single particle. Here this term denotes the internal force. This is the force acting on ith particle because of other remaining j particles. And the first term is the external force. This is the simple Newton second law, F is equal to dP by dt. Here Fij is the internal force on ith particle due to jth particle. Here I am not using, here I have used J not equal to I, which means that when J will be equal to I will be having this expression as Fii, which means force acting on ith particle due to ith particle, which obviously is 0. Therefore, I have written J not equal to I. Now this is the expression for a single particle. Now I will modify this expression to n number of particles, that I will sum this expression for n number of particles. Here I have taken the sum of this expression. The force, external force has been summed and the internal force has also been summed. But I will show that internal force is 0 because according to the Newton third law, the force expressed by ith particle on jth particle will be equal and opposite to the force acting on jth particle due to ith particle. That is, Fij will be equal to minus Fji. Hence, this term Fij will be, summation of Fij will be 0. Here the prime denotes that I cannot be equal to J because no particle exerts force on itself. So Newton law, second law is summation Pi naught is simply equal to summation of external force acting on the particle. Now I am using the definition of center of mass. Center of mass is defined as average of radii vector of particles which is weighed in proportion to their masses. That is, capital R is equal to summation mi upon summation mi. Here summation mi represents the total mass of the system. Now I am putting my expression, Newton's second law expression, in terms of capital R, that is center of mass. So my Newton's second law becomes m d2r upon dt square is equal to F external When it is written in the form of linear momentum, total linear momentum will be equal to mr dot. Now, as I have earlier said that I have derived the conservation law of linear momentum for single particle. Now I am extending it to a n number of particle system. Since we have P is equal to mr dot, differentiating this expression, we will get P dot is equal to mr double dot, and here we have shown that this is equal to F external. So we can arrive an important conclusion that when force acting on the particle is 0, P naught will be 0, hence we will get P to be equal to constant. This shows that when external force acting on a n number of particle system is 0, linear momentum will be conserved. Since P is constant, here putting P to be constant, we will get as m is constant, r naught will be constant. As I have already stated that r is center of mass. So r dot will be the velocity of center of mass. Now since p is constant, r dot is constant, that means center of mass in this case will move with constant velocity when there is no force acting on the particle. An important example of this is the radioactive disintegration of nuclei. Here I have shown a nucleus which is undergoing disintegration. It is moving with a constant velocity. When it undergo disintegration, different particles are produced. This is the product nucleus. A proton or electron and a neutrino will be emitted, and it has been shown that even after disintegration, the center of mass moves with constant velocity. Because the explosion has occurred in the absence of any force, F is 0, hence P will be constant. P constant means R dot will be constant in this explosion. This is a very good example of conservation of linear momentum. Now moving over to the second law, that is the conservation theorem for angular momentum. We know that angular momentum of the system is r cross p, ri cross pi. This is the expression of angular momentum for ith particle. But here we are having a n particle system. For n particles, we have to sum this expression. So I have summed this expression for n number of particles. This is the relation for derivative of angular momentum d by dt ri cross pi. Opening this expression, differentiating this expression, I get ri cross pi dot plus differential of first term, that is ri into pi. Here second term, that is ri dot cross pi, this term is 0 because we know that p is the linear momentum and linear momentum has a value equal to mv. V means ri dot. So I get ri dot cross ri dot, and cross product of this term will be 0. I get only first term, and I have already written that pi dot is equal to external force plus internal force. So here I get the first term is the external torque and the second term is the internal torque acting on the system. Now I will show that as the internal force acting on the particle is 0, similarly the internal torque, which is represented by N internal, this will be also 0, as expressed by the expression internal torque is Ri cross Fij. Now I am extending this expression Ri cross Fij. I have simply changed the indices I to j. You can see Ri, here I have written it is Rj and Fij. By changing the indices, it can be simply written as Fji, as it makes the no difference. Now since both are equal, I can express it as sum will make them double. So here I have put on half outside. So these two expressions are similar in value. Now since I know that according to the Newton's third law of motion, Fij, which is the force acting on ith particle due to jth particle, is equal and opposite to force acting on jth particle due to ith particle. Using this relation Fij to be equal to minus Fji, substituting this, here I get the internal torque to be half summation ij prime Fij. These two are opposite, hence minus sign arises here. Ri minus Rj. This is the vector Rij, whose direction is from the particle j to I. Hence, both the direction of these vectors, this is Rij and this is Fij, direction of these vectors are parallel to each other and the cross product hence will be equal to 0. So internal torque arising from the n particle system will be 0, which I have which I have written as n internal will be equal to 0. The internal torque hence vanishes. The only torque that is we are left with is the external torque. Hence dl upon dt, which is equal to sum of external torque. So here we can derive the law as when external torque is 0, angular momentum of the system will conserved. Hence n external is 0, L is constant in time or conserved. As similar to the single particle system, here in the n particle system, we have approached in the similar way that when force will be 0, angular linear momentum will be conserved, and when torque will be 0, momentum will be conserved. We are left with the third law, that is the conservation of energy, that I will deal in the my next lecture. I hope you all must have understand what I taught today. Thanks a lot.